Hello. Here we are, the last derivative, the last thing you have to learn how to take derivatives of. Save the best for last, the inverse trig functions. Not just trig, inverse trig. I have great news for you. They're ugly, but just like the trig functions, you memorize them and that's the end of it. Right, so in this section, I just want to show you, I'm going to show you the derivation of one of them so that you can see where they come from, because they're a little bit strange. Once you see how we get them, you don't ever have to do that again. I just want you to know where they come from, and then I'll give you the formulas, and unfortunately, yes, you have to memorize them. Well, sorry. Just in case you're wondering, when I Googled inverse trig functions, this was one of my pictures. And years ago, a student named Alexi that almost never spoke, I think he graduated CMU a few years ago. He almost never spoke, and when I put this slide up, he says, "Why does it say inverse phoenix on that dumpster?" And so that's the day we learned that that apparently is Russian for inverse phoenix, which I guess is why it came up when I typed inverse trig. It's good times. All right, you ready? Last derivatives I'm ever going to teach you how to take. Here we go. Okay, so what we want to be able to do is find the derivative of not just the sine of x, but the inverse sine of x. In other words, the function that says, okay, here is not just a function. The sine says, here's an angle, give me its sine, right? We want you be able to do the function of, here's the sine of an angle, what was the angle? Right? Or here's the sine of a number, what was the number? That's a different derivative. Unfortunately, the derivative of inverse sine x isn't inverse cosine x. Sorry. Okay. What we're going to need to do here is employ a little bit of rewriting and a little bit of implicit differentiation to get where we need to go. All right, now, again, I just want to show you where this came from. You do not need to write this down. You're certainly welcome to. Generally in class, I tell people they have to put their pencil down. They are not allowed to write this down. They are only allowed to watch me and listen, and that makes some people very anxious that they're not allowed to write it down. So if you feel like you need to write it down, by all means, but this is nothing that I'm going to ask you to reproduce. This is nothing that AP is going to ask you to reproduce. I just feel like it's important that you know where these come from. All right, so let me show you how we get the derivative of an inverse trig function so that we can never do it again. All right, so I have y equals the inverse sine of x. So the first thing I'm going to do is I'm going to rewrite that as something I know how to take the derivative of. So knowing what an inverse sine is, I'm just going to rewrite that as, instead of inverse sine of x equals y, the sine of y equals x. It's just a rewrite based on what we know inverse functions do. Now that I have it written like this, I can take the derivative implicitly because I know the derivative of sine and I know the derivative of x. So if we take our derivative implicitly, the derivative of the sine of y becomes cosine y dy dx, and the derivative of x becomes 1. We do a quick little algebra and we get dy dx equals cosine of y, or 1 over cosine of y, I'm sorry. Now, you may be thinking, well, that was easy, we're done, right? One problem. This equation was given to us explicitly, y in terms of x. So our job is to return an answer, dy dx, in terms of x, not y. So we have a little bit of work to do to change this cosine y into something in terms of x. Now, it may not be something you'd think of on your own. Frankly, I would have never thought of this. But it's a pretty simple way to do it. So check this out. We know for a fact that sine squared plus cosine squared of any angle is equal to 1. It's like the one trig identity everybody remembers. Right? So I know that sine squared plus cosine squared equals 1. Well, I just happen to have a cosine here. So if I solve this trig identity for cosine of y, I get the square root of 1 minus sine y. Well, that's still not terribly helpful because this is still in terms of y. However, I know what the sine of y is equal to. The sine of y is equal to x. I know that because of the equation I was given. I was originally given this, and I immediately wrote it as this. So I know what sine y is equal to. Sine y is equal to x. So I am allowed to replace this sine of y with an x. In other words, I'm allowed to replace this sine squared of y with an x squared, because I know this identity is true, and I know this is true in this particular situation. So by doing that, I rewrite this derivative. Instead of cosine y, I'm going to be rewriting it in the denominator in terms of x. So my cosine y becomes the square root of 1 minus, instead of sine squared y, x squared. And this is the formula that we're going to memorize. So I told you they were strange. When you take the derivative of an inverse trig function, it doesn't end up having a trig function in it, which feels a little strange. Now, this is the basic rule. Notice there's no chain rule here, there's no cloud, there's no baby. But this is the kind of just basic one. So what I want to do is show you the formulas. They're going to have u's in them. Remember, u's are just clouds. And there's 6 because we have 6 trig functions. They are all similar. They're all rational. None of them have any trig functions in them. But they also follow some similar patterns that we have seen before. Okay, so here is my inverse sine rule in terms of u. In other words, in terms of a cloud. Let's use blue for clouds. Blue clouds smiling at me. There we go. So if I have the inverse sine of a cloud, I'm literally just rewriting that. There's nothing to do really but have this formula memorized and then keep our friend the chain rule in mind. So if I have the inverse sine of a cloud, it's 1 over the square root of 1 minus cloud squared, and then chain rule. That's your cloud prime. That's it. You just have to have it memorized. So for example, if I'm given the inverse sine of 1 minus 2x, I say, okay, I know what that derivative is. That's 1 over the square root of 1 minus this cloud squared. So 1 minus 2x quantity squared, and then I'm going to chain rule my cloud, so minus 2 out there. Now, you could FOIL this out and do some simplification under here if you wanted to. That's not necessary. You could pop this negative 2 into the numerator. That's fine too. Okay. But again, when it comes to inverse trig derivatives, there's really nothing to be done but memorize them and remember to chain rule. All right, let's take a look at the other ones. This is a reference to the show Lost, which is probably getting way too old, but if you watched Lost, there are 2 groups of people on an island, and the good people that we love, find the other people and they call them the others. And they're scary and bad. So I think it's hilarious to call these the others. At least I think it's funny. All right, here's your sine derivative, right? Now, remember what we learned about co-functions? We learned about derivatives, that they're always negatives. Check it out. The derivative of the inverse sine is 1 over square root of 1 minus cloud squared. Look at the derivative of inverse cosine. Literally the only difference is a negative. So if you know the inverse sine derivative, you know the inverse cosine. All you gotta do is pop a negative on it. Which makes sense if you think about that derivation we just did. If we had started instead of x equals sine y, if we had started with x equals cosine y, the only difference in our problem would have been a negative. Okay, ready for the next one? This is tangent. Tangent is a sneaky one, and he comes back in a later section to bite us if you don't memorize tangent, because when we start doing backwards derivatives or integrals, tangent shows up sometimes, and so does sine actually a lot, and cosine, and we don't immediately recognize them as inverse trigs, and we try to do other stuff with them. So I know I've said this before, and I'm going to say it again. It's really actually important that you memorize these, because you need to be able to recognize them when you see them so that you don't waste time trying to do other stuff. Okay, so there's tangent. No square root here. It's just 1 over 1 plus your cloud squared. That's it. So cotangent is literally that with a negative on it. That's it. Okay. Last one. Oh, secant. Secant, of course, has to be the crazy one. Right? Secant has an absolute value of u in it. So if you're taking the derivative of the inverse secant, it's 1 over the absolute value of your cloud and then square root of cloud squared minus 1. So it's the exact opposite of sine here under the root. And then it has this absolute value of u. And then good news, cosecant. Same thing with a negative on it. So there's not really 6 to memorize. You really only have to memorize these 3. And then once you have these 3, remember that their co-partners are just negatives. All right, so I want to just do an example or two just to show you, how to use these. Because again, there's not much to it other than memorizing. Memorizing and remembering the chain rule. That's it. Just got to do it. Don't forget the baby. Okay. Okay, so let's not forget the very first rule we ever learned for derivatives, and that was that sum and difference rule. Here we have 2 quantities and they're being subtracted. So I'm taking their derivatives completely separately. At a glance, if you look at this, you might be a little overwhelmed by it because it looks like a lot. But again, anytime you have plus and minus signs, those are separators, right? Those are walls. I'm taking the derivative here, I'm taking the derivative here. I'll worry about, then I'll just subtract them when I'm done. So I need to take the derivative of x squared minus 1 square root, which is kind of old news, and then here's my new derivative over here. Okay, so first things first, let's get the derivative of that square root of x squared minus 1, because that's the easy one, right? All right, so it's a square root, so I'm going to rewrite it as an x squared minus 1 to the 1/2. So my derivative is going to be a 1/2 x squared minus 1 to the negative 1/2, and then I'm going to chain rule 2x. Okay, minus the big minus sign. Let's take care of our secant. Now, I have memorized my secant derivative to be 1 over the absolute value of my cloud, square root of my cloud, squared minus 1. That's a formula I memorize. So all I have to do is go up here. I see inverse secant. Fine. Find your cloud, pop it in down here. This is going to be the absolute value of 3x squared, and then chain rule the derivative of your cloud times 3, and that's it. Now we can clean it up a little bit, right? So over here, my 1/2 and my 2 can go away, and I can say this is x over the square root of x squared minus 1. Here I'm going to put my 3 up top, absolute value of 3x. And then 9x squared minus 1. Now I simplify this because I do want to show you something that you will see in simplifications, and please don't be alarmed by it. This absolute value of 3x can easily be written as 3 times the absolute value of x, because the 3 is itself positive, so pulling it out of its absolute value has absolutely no effect. And by doing that, you can then cancel that 3 with the 3 up here. So if you're checking answers and you see that you had like a 5x and a 5 and they're gone, right? That's what happened. This is an absolute value of 3 times the absolute value of x. You can write them separately if you want to. And then the absolute value of 3 is just 3, and they can cancel out. So maybe do keep that in mind. Dare I say that you have to keep in mind that this isn't, that you can't like take the square roots of these things individually and call this 3x minus 1. Oh God, please. Please don't do that. Right? This is a difference of 2 squares. This factors to 3x plus 1 and 3x minus 1. But since those are 2 different quantities, I can't simplify anything. So do be careful with that. Don't get excited and start oversimplifying. But you will see this periodically with the secant. Okay. Here's one with a tangent. Tangent's my favorite, I guess because it doesn't have a square root. Now notice here, I don't have a difference. I have a product here. So that's fun. So let's do our product rule. Okay. I am going to, I don't want to use a cloud. What shape can I use? I'm just going to circle it, oval it, ellipse it. Okay, so since I'm using a product, I'm doing this because I want to write it out so we don't get too confused. I am going to take the derivative of my square, forgot my shapes for a minute, multiply by my ellipse plus the derivative of my ellipse times my square. So when I get the derivative of my square, that's no big deal, right? That's 1/2 5x to the negative 1/2 chain rule times 5. When I take the derivative of my ellipse, that's an inverse tangent. Okay, now I know the rules for the tangent, memorized it. It's just 1 over 1 plus u squared. So all I really have to do is find my u. It's going to be 1 over 1 plus whatever my cloud is squared. And then, of course, chain rule. So I have here inverse tangent of 3x squared, so my cloud is 3x squared. So this derivative is going to be 1 over 1 plus 9x to the 4th, and then I have to chain rule. So the derivative of 3x squared is 6x. Word of caution, I squared this, right? I could have just written this as 1 plus quantity 3x squared squared. And that probably would be wise, right? Because then I don't risk making a silly mistake here and writing like 6x to the 4th. But also one of the things that I tend to see people do is once they square this, when they chain rule, they accidentally, instead of chain ruling 3x squared, they chain rule 9x to the 4th, and so they write 36x cubed out here. And you don't want to do that. The chain rule is the derivative of your cloud, not your cloud once it has been squared. So be careful with that. So in this case, my derivative, it's a doozy. Let's see, I can write this as 5 over 2 square root of 5x times my inverse tangent. And then plus my inverse tangent derivative, which is 6x over 1 plus 9x to the 4th times my root 5x. There it is. Ooh. Again, you could bring that over into the numerator. There's not a whole lot you're going to be able to do simplification-wise here. But why would you want to? Look at that beautiful answer. Let's see. Okay, let's do one more, shall we? Ooh, an inverse cosine. Ooh! What else do you see here? I spy with my little eye implicit differentiation. Because this stinking thing is not written y equals. So this is implicit. Oh well, we'll do implicit differentiation. It just so happens to have an inverse trig in it. That's fine. We're good at both things. Okay. So I need to take the derivative of cosine, which, great news, is exactly like the derivative of sine with that one exception. So here's my cloud. The derivative of cosine, instead of 1 over, is going to be negative 1 over the square root of 1 minus u squared. So parentheses x squared minus 7, that whole quantity squared. And then chain rule 2x plus the square root of y. I need the derivative of that. So that's 1/2 y to the negative 1/2 dy dx equals the derivative of 8, which is 0. So we've got a little bit of algebra to do here. Where's my algebra people? All right, let's see here. I'm going to put this 2x up top just to try to make that a little bit easier looking. And then here, I'm going to write this as a 1 over 2 square roots of y. Well, this isn't going to be too bad algebraically. If we move this to the other side, it just becomes positive on this side. And then all I have to do is multiply this to the other side. So I get dy dx equals, when I multiply this to the other side, it's going to pop into the numerator, right? So instead I'll have a 2, an x, and a root y. So I'll have a 4x squared y all over 1 minus x squared minus 7 squared. Wait, square root right here. And there she is. As pretty as she can be. At least there wasn't a product rule in here. I just had this overwhelming fear that I forgot the baby, but I didn't. I'm good. I'm good. Okay. All right. So that's inverse trigs. Like I said, there's really nothing to do but memorize them. I'm sorry. I know you don't like memorizing. I don't either, but it is what it is. Again, I know that for now we're online and I can't look over your shoulder and you can just write them down and have them in front of you. But again, it is coming. The day is coming where you are going to be looking at a problem and your job won't be to take the derivative. Your job will be to say, I know whose derivative that is. That's the derivative of an inverse tangent. So you have to know them well enough to recognize them when you see them. And that's like a new level of knowing them because you can't go glance back at a formula, right? You have to know them well enough to recognize them when you see them. Otherwise, you're going to waste a whole lot of time and I promise you, you're going to have a really hard time in integrals. Please listen to me now. Don't struggle later. Just memorize them. Okay. Make sure you note any questions you have, and we will talk soon. Bye.